Section 3.9, derivatives of logarithmic and exponential functions. We're going to use what we know about the properties of logs and exponents and our derivative rules to develop formulas for the derivatives of exponential and log functions. Some properties that we're going to use throughout this section are that e to the natural log of x is equal to x. E and the natural log are inverse functions of each other, and so they undo each other when applied to x. E to the natural log of x equals x. For x greater than 0, natural log is only defined for values of x greater than 0, and vice versa, natural log of e to the x is equal to x because those functions are inverses of each other. Similar property, y equals natural log of x if and only if x equals e to the y. And so we could take e and raise both sides to the, or take e and raise it to both sides of this equation. E to the y equals e to the natural log of x. And so e to the y is equal to e to the natural log. Those undo each other, so that's just equal to x. So we get x equals e to the y. And then last, b to the x equals e to the natural log of b to the x. Again, e and natural log undo each other. So if I take the natural log of b to the x and then I apply e to that, those would undo each other, and this is just equal to b to the x. And then a rule of logs is that when you have an exponent inside a log, you can bring that exponent down in front of the log, and so you get e to the x times the natural log of b, and we'll be using those properties throughout this section. So let's use what we know about implicit differentiation and the properties of exponential and logarithmic functions, and let's develop the derivative of the natural log of x. And so we just wrote down that if we know that y equals the natural log of x, and if we take e and raise, say, e to the y equals the so let's write that in another line. E to the y equals e to the natural log of x. If we apply that e to both sides, then we get e to the y is equal to x. So this equation and this equation keep the same relationship between x and y. They're just written differently. So let's start with x equals e to the y, and let's use implicit differentiation to find the derivative of that. Derivative of x is just 1. Derivative of e to the y is e to the y, but now I need to take the derivative of the inside of this. The inside of this is y, so the derivative of that would be 1, but since we're taking the derivative with respect to x, we would get a dy dx. Solve for dy dx. We would end up with dy dx equals 1 over e to the y, just dividing by e to the y on both sides. And then e to the y is equal to x from this step, so we can say dy dx is equal to 1 over x. And so we get the property that the derivative of the natural log function is equal to 1 over x. And if we do a little bit more work, we can get the derivative of the natural log of the absolute value of x is equal to 1 over x. Remember that this is only defined for x greater than 0. This function would be defined everywhere except for x equals 0. And then we can also use the chain rule when we're taking the derivative of the natural log function. And so we would get 1 over whatever's inside of here times the derivative of whatever's inside of here. And we're going to do several examples. We're going to do these 4 examples. Again, if you want to skip over the examples and then come back to them when you're doing your homework, that would be an appropriate thing to do. Or you can listen to the examples and then go do your homework. All right, so we have y equals 3x cubed times the natural log of x minus x cubed. So all of our other rules still apply. Here we have a product of 3x cubed and the natural log of x, and then we're subtracting x cubed. Dy dx. We're going to use the product rule first. Product rule says take the derivative of the first, 9x squared, leave the second, add to that. We're going to leave the first and take the derivative of the second. We now know that the derivative of the natural log of x is equal to 1 over x. And then we need to take the derivative of x cubed, which is 3x squared. Now, in this section, and in many of our sections, we know how to take the derivative. If you're interested in getting to the solution that the book has, they're going to have you do a bunch of algebra and simplification. I'm not sure exactly what happens when you enter this in MML, if they would accept this as an answer or if it wants you to simplify. In either case, I'll go through the simplification with you. This looks like 9x squared natural log of x. That looks like 3x cubed divided by x is 3x squared minus 3x squared. So I think I end up with just 9x squared natural log of x because those two would cancel each other out. Y equals the natural log of x plus 1 over x minus 1. Y prime, or dy dx. Derivative of the natural log of anything is 1 over that anything times the derivative of that anything. So the derivative of that anything, we're going to use the quotient rule, which is low d high minus high d low all over low squared. And then we can do some algebra to simplify this. I'm going to 1 over this is going to flip it over, so I'm going to flip that over. This gives me x minus 1 minus x minus 1 all over x minus 1 squared. Leave this, x minus 1 times x plus 1. X minus x gives me a negative 2. Negative 1 minus 1, negative 2 over x minus 1 squared. You can cancel out that with one of those. I'm left with negative 2 over x plus 1 times x minus 1 equals negative 2 over x squared minus 1. Sometimes your book does some shifting around with this. If I factor out a negative here in the top and a negative in the bottom, that will leave me with a positive 2 on the top, and that'll reverse the order of the bottom. So those two things are equivalent. I would take either answer. Y equals the natural log of the natural log of x. This one we're going to use the chain rule. Start with the natural log of the natural log of x. So when I take the natural log of anything, I get 1 over that anything. So I'm going to get 1 over the natural log of x, and now I need to multiply times the derivative of the natural log of x, which is just 1 over x. So we could write this as 1 over x natural log of x. Y equals the natural log of x cubed plus 1 to the pi power. They often try to freak you out with putting weird exponents here, and we're going to deal with it just like that was a regular number. Properties of logs is that if you have an exponent inside the log, you can bring it down in front of there, and those are equivalent. And now I can take the derivative of this. I get pi as a constant. I can multiply times the derivative of natural log of x cubed plus 1. Derivative of natural log of anything is 1 over x cubed plus 1, 1 over that anything, times the derivative of that anything. So I'm going to get 3x squared. We could simplify this to say maybe 3 pi x squared over x cubed plus 1. What we're going to do now is take the derivative of functions with bases other than e. So we know that if we have the function y equals e to the x, the derivative of e to the x is e to the x. But if I have something like y equals 2 to the x, the derivative of 2 to the x is not just 2 to the x. And we're going to use this formula that they tell us first, this theorem that they give us, and then we're going to figure out where this theorem comes from. So this tells us the derivative of 2 to the x, some base, is equal to that base times the natural log of that base. When we take the derivative, dy dx, we get 2 to the x again, so we're writing 2 to the x again, and then we multiply times the natural log of 2. This works for any base, even if we have y equals e to the x, which we know the derivative of y equals e to the x is e to the x. But using this theorem, we get e to the x times the natural log of that base. But the natural log of e is just 1, so this is e to the x. So this theorem works for any base. Let's see where that theorem comes from. So let's use instead of b to the x, let's use 2 to the x. And if I want to rewrite 2 to the x using e, because I know how to take the derivative of something with e in it, I could say I'm going to take the natural log of 2 to the x, but I'm also going to apply e to that, so I get e to the natural log of 2 to the x. E and natural log are inverse functions, so this is still equal to 2 to the x. Now let's say I want to take the derivative of this e to the natural log of 2 to the x. Well, our log rules say that I can rewrite that as d dx of e. I can bring this x and sit it down in front, x times the natural log of 2, which I could write as e times the natural log of 2 times x. Let's go think over here. If I have y equals something like e to the 3x, the derivative of e to the 3x would be e to the 3x times the derivative of the inside, which would be 3. So let's use this idea. This is an aside. That's not part of this problem. Let's use that idea here. The derivative of e to the natural log of 2 times x is going to be e to the natural log of 2 times x times the natural log of 2. Just like we did here, we had to multiply by 3. Here we have to multiply by the natural log of 2. Well, we just figured out that e to the natural log of 2 times x is equal to 2 to the x. And so that derivative is equal to 2 to the x times the natural log of 2. And if we want to add the notation, this is d dx of 2 to the x is equal to 2 to the x times the natural log of 2. And we're going to do several examples using that. 2 examples, y equals x cubed times 3 to the x, y prime. This is a product of 2 functions, x cubed and 3 to the x. Take the derivative of x cubed, we get 3x squared, leave 3 to the x, plus leave the x cubed, multiply times the derivative of 3 to the x. The derivative of 3 to the x is 3 to the x, but we multiply times the natural log of 3. Now here, your book may do a little bit of factoring things out. I see a 3 to the x in both of these. I also see an x squared that I can take out of those. And so I'm going to take out an x squared 3 to the x. And when I do that, that goes away. I'm left with just 3 plus x natural log of 3. And I'm not sure what your book says the answer is, but I would accept both of those. Next, y equals 2 to the 3 plus sine x. Take the derivative of that, y prime. Derivative of 2 to the anything is 2 to that anything times the natural log of 2 times the derivative of that anything. So the derivative of 3 plus sine x, derivative of 3 is 0, derivative of sine of x is cosine of x. And so we can leave that as the answer, 2 to the 3 plus sine x times the natural log of 2 times cosine of x. Similarly with log functions that have different bases than e, natural log is a log base e. We take the derivative of those functions differently. So if I have log base b of x, I'm going to use something called the change of base formula to change this into a function with natural log in it. Change of base formula says that this is equal to the natural log, if I'm changing to the base e, natural log of this over natural log of that. And this really could be any base that you could put here. You could put log base 2 of x over log base 2 of b, but since we know what the derivative of the natural log of x is, we're changing to natural logs. Now what I like to do is write this as 1 over the natural log of b times the natural log of x. This is going to be a constant, and this is your function of x. So when I take the derivative, I can leave this constant out in front and just take the derivative of the natural log of x. So let's do an example. Let's say we want to know the derivative of log base 10 of x. And I'm going to call that y equals log base 10 of x. Using the change of base formula, I can write that as 1 over the natural log of 10 times the natural log of x. And so then I can take the derivative. The derivative is going to leave this constant, 1 over the natural log of 10. I can type that into my calculator. It's just a number. And I'm going to multiply that times the natural log of x, which is just 1 over x. And so the derivative of log base 10 of x is 1 over natural log of 10 times 1 over x. And if you want to write it like they have it in this form, we could just say that's 1 over x natural log of 10. We did the log base 10 of x. We're going to do y equals log base 8 of tangent x. Use our change of base. This equals 1 over the natural log of 8 times the log of the absolute value of tangent of x. Y prime, we can just leave this natural log of 8 in front and multiply times the derivative of natural log of tangent x. 1 over tangent x, derivative of natural log of anything is 1 over that anything times the derivative of that anything. And we could do some simplification here, but I'm just going to leave it like this. Last thing we're going to look at is something called logarithmic differentiation. So this function that we have here is something that we could take the derivative of using our rules that we already know before this section, We could use the chain rule within the quotient rule, and that would work out fine. There's another way to do this derivative. It makes it maybe a little bit cleaner, but in some ways it's just a different way. And when we're using logarithmic differentiation, instead of writing f of x, I like to write y. You can leave it as f of x if you want, but I think it makes it a little bit cleaner to write y. So first thing we're going to do is we're going to take the natural log of both sides, and you'll see why we do that in just a second. My dog is barking. We're going to use our log rules to rewrite this in a little bit simpler form. So first thing we can do with our log rules is division with log rules is the equivalent of subtraction with logs. So we can say x plus 1 to the 10th, the natural log of x plus 1 to the 10th, minus the natural log of 2x minus 4 to the 8th. And you could combine that in one step, this in one step once you get to that point where you're going a little bit faster. Log rules also say I can move this 10 down and this 8 down in front. So I get 10 times the natural log of x plus 1 minus 8 times the natural log of 2x minus 4. Now we're going to do our implicit differentiation. The derivative of the natural log of y is 1 over y, but since we're taking the derivative with respect to x, we're going to multiply by dy dx. The derivative of this is, we're going to leave the 10 out in front. That's just a constant, so you can leave it out in front. The derivative of natural log of x plus 1 is 1 over x plus 1 times the derivative of x plus 1, which is just 1. Here we're going to get 8 over 2x minus 4. 8 times, I could write that as 8 times 1 over 2x minus 4 times the derivative of 2x minus 4, which is just 2. So I wrote this one a little bit different than this one. I should have probably written 8 times 1 over 2x minus 4 to be consistent, but those mean the same thing. So we get 10 over x plus 1 minus 16 over 2x minus 4. And then the last step is we don't want 1 over y times dy dx, we want just dy dx. So we're going to multiply both sides by y to get rid of this. So when I multiply this side by y, I get just dy dx. And I get y times all of this stuff. But I also know what y is. Y is equal to this stuff on the top, x plus 1 to the 10th over 2x minus 4 to the 8th times 10 over x plus 1 minus 16 over 2x minus 4. I can just write that with one big parenthesis. Now I'm sure that your book does some more algebra here. I'm just going to leave it like this and leave you to the algebra. Last type of problem we're going to do is something they call a tower function. I've not ever heard that vocabulary before, but you can go to page 213. They do these problems slightly differently than I do, so you can look at 213 in your text and see the difference between the way that I do it and the way that your book does it. Anytime that you have something that has an x in the base and an x in the exponent, you're going to want to get those away from each other. We don't know how to take the derivative when we have x in the base and x in the exponent. And we're going to use logarithmic differentiation. Again, I'm going to do number 50. And instead of calling that g of x, I'm going to say that's y equals x natural log of x. And a way of getting natural log of x, or an x out of the power, is to take the log of both sides. And we know about natural logs, so we're going to take the natural log of both sides. Again, with natural logs, I can take that exponent and bring it out in front. So I get natural log of y equals natural log of x times the natural log of x. If I want to, I can use the product rule here, or I can write this as natural log of x, the quantity squared. Notice that's different than natural log of x squared, where the x squared is inside the log. Now I can use my implicit differentiation. Derivative of natural log of y is 1 over y dy dx. Derivative of this is 2. I'm going to bring that 2 down in front, leave the inside alone, decrease that exponent by 1, so that would be natural log of x to the first power, times the derivative of the inside, which is just 1 over x. I'm going to multiply both sides by y to get rid of this, so I get dy dx equals y times 2 natural log of x all over x. And then I know that y is equal to x to the natural log of x times 2 natural log of x over x. And at this point, I would probably leave it like this. I think your book takes one more step. they write this as, well, kind of two more steps. They put this x natural log of x over x times 2 natural log of x. When I have the same base, this is like x to the first, when I'm dividing, I can subtract those exponents. So your book might write this as x to the natural log of x minus 1 times 2 natural log of x. I tend to leave it like this. I don't think that this is all that simpler than the way that I have it. This section had a lot of pieces in it. We figured out what the derivative of the natural log of x is. We figured out what the derivative of an exponential function with a base other than e. We figured out that derivative, and we figured out the derivative of a log function with a base other than e. And so we learned those things, and on top of that you have all your other derivative rules and then the algebra that's associated with that. So this practice is going to use those 3 new things that we learned, but we're going to keep practicing all of our other derivative rules. And life wouldn't be the same if I didn't tell you you had MML section 3.9 and the section 3.9 quiz. Again, make sure you're asking questions, and I'm here to help.